Today, I want to start by just reminding you of the way that we're thinking about integration. Integration is going to be our next big thing. It's going to show up next week. We're going to talk about integration. What we're going to be doing is upgrading integration from functions of one variable to functions of two variables. That's where we'll start. And then we'll go on to functions of three variables. And then we'll even go on to vectors. But we want running in the background how we think, this thinking about integration. Integration is multiplication, but one of the factors is variable. I want to calculate area as length times width, but the length keeps changing along the width. So then we have to integrate. That drops multiplication back down to addition. Integration is just addition. We're adding up a bunch of values of the function. Remember that definite integral comes from a Riemann sum where we're adding things up. But the Riemann sum, the delta x is going to 0. So we're turning our discrete addition into a continuous addition. That's what I want running in the background. Put that in your subconscious early. And then when the problems actually start showing up on Monday, we'll have at least this basis in how we think about things. So we don't look at the stuff that we see in chapter 16 as being brand new. It's just old stuff that we're modifying. All right. So let's finish up our problems from chapter 15 with our constrained optimization. We want to find the minimum distance from a point to this paraboloid, x squared plus y squared equals z. So in this problem, we weren't explicitly given the objective function. We want to find the minimum distance. So distance is our objective function. That's the first thing we notice. We weren't given a function, f of x, y, z, to be our objective. We were just told find the minimum distance. This tells us that here is our objective function. Because that's the thing that we want to minimize. That makes this our objective. So our objective function is going to be a distance function. From the point 248, so here's another thing that we notice. From the point 248, looks like our objective function is going to have three variables. Orange is not constraint, constraints are green. And we want to find the minimum distance from this point 248 to the paraboloid given by z equals x squared plus y squared. So here is our constraint. We're trying to be close to this point. The next thing we need to note, so what we need to write down is a function for our distance. It's the distance between the point 248 and some generic point x, y, z on this constraint. So we have to build our own objective function. It's going to be a function of three variables. And it's going to be the distance between 248 and some point x, y, z that fits this description. So I'm just going to write down the distance formula. From some point x, y, z and the point 248. So it's going to be x minus 2 squared plus y minus 4 squared plus z minus 8 squared. So here is our objective function. The distance from the point x, y, z on the parabola, or the paraboloid, and the point 248. Now we're going to notice something. We're going to think about this problem. We know one of the things we have to do is make the gradient of our objective and the gradient of our constraint line up. We want those pointed in the same direction. And if we want the gradients to point in the same direction, we're going to need to take derivatives. And now I'm looking at my function f of x, y, z, which is the distance. This is just the distance from a point x, y, z on the paraboloid to the point 2, 4, 8. So f of x, y, z is the distance from some point x, y, z on the paraboloid to the point 2, 4, 8. We just use the distance formula for this, and here's what we don't like. I need the derivative of this function. So I'm going to have to take this sum of 3 squares to the 1/2 power. And I'm going to have 1/2 times all that stuff to the negative 1/2 times the derivative of the inside, which would thankfully just be 1. Or no, sorry, 2. This is going to be awful. So here's the problem that we run into. We need fx, fy, and fz. Some of you is looking at this and saying, oh God, I see where this is going and I don't like it. And I'm like, oh, I know, right? If you're not seeing it yet, so fx at x, y, and z, all this is to the 1/2 power, so I'm going to have a 1/2 of all this stuff to the negative 1/2 power. And then I have to multiply by the derivative of the inside with respect to x. The derivative of x minus 2 squared is 2 times x minus 2 to the first. Thankfully, the y and the z's terms are going to be constant with respect to x. So all of a sudden, I'm having to start. Oh, at least the 1/2 and the 2 cancel out. So there's, thank goodness for that. But this is what we're going to have to put in our equations. Oh, it's not even an equation. We're getting a system. So we don't want this in our system of equations. So we're going to do an old math trick. Instead of minimizing the distance, I'm going to minimize the square of the distance. So let's be sneaky. Instead of minimizing the distance, these are the sleepiest pens. That one's just not going to work. Instead of minimizing the distance, we're going to minimize the square of the distance. We're calculating a distance. The problem is the expression involves this square root, which makes our derivatives really messy. But if we look at the square of the distance, if I rewrite my function, capital F of x, y, and z. If I square it, I remove that big messy part. X minus 2 squared plus y minus 4 squared plus z minus 8 squared. This is much nicer. So we'll have to remember that this is the square of the distance and not the actual distance. But if we find the minimum square of the distance, we just need to take the square root, and that will be the minimum distance. This works out because we're worried about distance, which is always positive, and the squared function, f of x equals x squared. That's an always increasing function. Bigger distance, bigger square of the distance. So that's the big trick in this problem. And that's the thinking that goes by. I didn't read the hints. Actually, let me just look. I have the problems right here. So the hint tells you what the objective function is, but the hint doesn't explain why this is the objective function. Books often take things to be obvious, which are totally not obvious to students. So this is the square of the objective function, and the reason that we're picking this is because the actual distance function has the square roots, and it makes for these awful derivatives. At least we don't need a second derivative. Because now our fx at x, y, and z, I'm using capital F, is just going to be 2 times x minus 2 to the first, and then plus 0. So that's why this is our objective function. The next thing that we have to deal with is that our constraint function is z equals x squared plus y squared. What I need is a function g of x, y, z. I need a function of 3 variables. So I'm going to take this paraboloid and I'm going to consider it to be a level surface of some function g of x. So I'm going to write g of x I'm just going to subtract the z from both sides. And I'm going to say g of x, y, and z can be x squared plus y squared minus z just. And my constraint will just be x squared plus y squared minus z equals 0. Because we want our constraint to be a function of 3 variables as well. So we need the constraint to be a function of 3 variables. Not just x and y. Because we're going to do Lagrange multiplier thing, we're going to need the gradient of our objective to be in the same direction as the gradient of our constraint. The objective function is a function of 3 variables. So we're going to need our constraint to be a function of 3 variables. Otherwise, there's no way to match the gradients. I believe the hint says to use this objective function and this constraint function. That's why. We're just minimizing the square of the distance because it's a cleaner derivatives than the distance. We can do this because the square function is always increasing. Bigger distance, bigger square. So if we minimize the square, we will be minimizing the distance. Any questions? So from here, I just started with derivatives to make the point that they're nicer. You still have to take all those derivatives. You still need your derivatives gx And we need to multiply your gradient of g by lambda. But that's why we're choosing this objective function. And that's how we reframe the constraint to be the level surface of some solid, so that we have a function of 3 variables. Any questions? At the end, don't forget to take the square root. When you find the minimum distance, when you find the minimum value of capital F, you need to take the square root of it so that you find the minimum value of the distance. You don't need to take the square roots of the x, y, and z. The x, y, and z don't care what we're trying to minimize. So at the end, when you find the minimum value of capital F, take the square root of that to get the minimum value of f. Don't do anything to the x, y, and z. We're not moving anything around. We're just changing the objective function. Just cheating a little bit. Classic math strategy. Trade one messy problem for a cleaner problem and then just modify your answer. Any questions? It's weird that the blue pen is not getting along with this page. Not equal to each other. Set the gradient of f equal to a constant, a constant times the gradient of g. Put the gradients in the same direction, and then solve like we did before. Yes, this is going to lead to a system of equations. And one of the ways you can analyze it is with multiple cases. It's a variation of the problem that we did yesterday, so I don't want to take all the fun out of it. I know some of you is wishing that I would take all the fun out of it, but I'm not going to take all the fun out of it. We can use the same strategy that we did yesterday. What values of lambda will work, what values of x will work, because we're going to have some weird things. Any other questions? So hopefully you can all see which problem I will not be finishing today. How's everybody okay? So you'll notice that we've been on a super long homework binge where we've been working on problems. This week, no new homework assignments have shown up because this week I wanted us to catch up because we're finishing up our derivative stuff so that we can move on into integration stuff. While we're working on integration stuff, we're going to be faced with some new problems from the derivative stuff. So I want to ask, one of the things that I tend to do is ask derivative questions that we haven't covered when I start writing quizzes. So this way, there are no derivative questions that I haven't covered. So when I go to write quizzes, I can just do whatever occurs to me. I can ask further along. So chapter 16 will not be due on Sunday. I'm going to move back the due dates for chapter 16 because I wanted to drop in another week to give people time to catch up on the first 4 chapters. Any questions? It's difficult to build due dates are always seeming very, very threatening because they're due dates. This is a deadline. But I know some of you have observed that deadlines in this class aren't that deadly. So if you miss a due date, if you go in on say Monday, say, oh, I didn't finish this homework, you can still do the homework problems. That's the way it's supposed to work. I don't want to set up a system where I stop you from doing problems. It's like that's the one thing that you want the students to do. You want them to do problems. But I also don't want to say the due date is December 10th, because some of you will put off 40 homework assignments till December 9th. And you'll wonder why your teacher is such a jerk because they won't give you an extension. For some of the this set of problems, I pulled out the solution section. Part of the reason is that there isn't an explanation in the solutions for why you would choose to use this objective function. This, just using this as an example, and this as your constraint function. So if you see the hint, that'll cause you to think about, well, why are we using this constraint, this objective function? Don't we need that square root to be the distance? Why is this the constraint function, x squared plus y squared minus z? Can't I just find the gradient of g with an I and a j? So it causes you to think about things a little bit more, which is what I wanted here. Any other questions? All right, so next week we're going to be starting on integration. Remember what the things that we need to think about with integration. Integration is multiplication, but one of the factors is variable. That means integration is just addition. Another way you'll see this is integration is accumulation. So if you consult Professor YouTube for some other viewpoints about integration, check out integration is accumulation. I like to turn things into operations, partially because I spend a lot of time teaching algebra, and so algebra is just operations. So think about those things, but not actively. Let it simmer in the background while you're working on finishing up, getting caught up with our first 4 chapters. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend, and thanks for playing.